Good morning, everyone. How's it going? Are you still sleepy? As Tom said, I'm Michaela, and I want to talk about ReactVR. So, reading the topic of my talk, you might have thought, a web in 3D? Isn't that nonsense? Isn't thinking and talking about a virtual reality web nothing more than ridiculous? And most of all, should I even care about ReactVR or WebVR? Well, as you may have guessed, I'm here to tell you that you should care about WebVR and ReactVR. Even if you are not a gamer, or even if you're just not into that virtual reality stuff, or even if VR makes you sick. Why, you ask? Because if this technology is permanent, and at the moment it looks like it is, because virtual reality will have a great impact on our users, and we all agree that we should care about our users, aren't we? So this is why I will tell you the most important facts about VR and ReactVR you as a developer have to know to create responsible virtual reality experiences. I'll begin with some brief general information about VR concepts, and then we'll have a look into the ReactVR library. And afterwards, I'll end with the topic I'm most passionate about, a good user experience in virtual reality web applications. Before I forget, you can all download the slides with the code and the links. I'll give you the URL at the end of the talk. So, since we only have 30 minutes, I won't talk about what virtual reality is. And I also won't talk about why I think VR matters. Instead, I want to concentrate on the things we as developers have to know when we want to create VR applications. So, let's begin with the concepts of virtual reality we need to be aware of if we do not want to exclude users. We'll begin with stereoscopic images. When we talk about stereoscopic images in the context of VR and the web, we are talking about two images next to each other showing the same content, but from a slightly different point of view. The offset of both images corresponds to the distance between our eyes and is called IPD, which means interpupillary distance. By showing these images to each eye, we are exactly recreating how we see the world naturally, and our brain combines these images like it always does and gives us the perception of 3D depth. When we are looking at WebVR images, we often do not see full-screen images like this, but some kind of distorted images like these. We need this effect to compensate the distortion the thick lenses are making to the images. If we didn't have the distortion, the image would look like this on the right. But if we apply a contrasting distortion to the original images, what we see behind the lenses will be without any distortion again. So, by showing two slightly different images to each eye, we are already getting an effect of depth. To make our brain believe that we are actually in a virtual space, we need to include tracking. Most VR devices have 3 degrees of freedom tracking sensors for the rotation around the free axis. And more advanced devices are also tracking the position of a user in a room, which is often called room scale VR. You can surely imagine that more tracking sensors intensify the feeling of actually being present in a virtual space. So this immersive feeling, of course, gets even stronger if we include input controllers with rotation or position tracking sensors in the experience. Now, how do we create such experiences in JavaScript for the web? Let me show you the stack we'll be working with. First of all, there's, of course, the browser. And then with WebGL, we have a JavaScript API for rendering GPU-accelerated 3D graphics in the browser. And to include access to the head-mounted display and its sensors, there's the experimental API WebVR. On top of this, there are often further JavaScript libraries. One common library to reduce the effort of writing WebGL is Free.js. And on top of Free.js, there's ReactVR. So Let me show you ReactVR in action with a super simple example. Here we have an equirectangular image that I captured with my full sphere camera, and what we want to do is show this spherical image in a stereoscopic way, and we also want to use the tracking sensors, more precisely the rotation sensors, to let the user look around. So our general setup could look like this. Here we see a three-dimensional coordinate system where the camera represents the user. And around the user there would be a large sphere, which would be our image canvas. To realize this with ReactVR, we are starting by installing the ReactVR CLI tool, and then we'll create a project which I called Geil Danke ReactVR Pano, and start a local development server just by running the npm script start. Let's take a quick look at the scaffolded project structure. First, there's the index.vr.js file that contains the application code we'll write to create the panorama. And then, of course, there's a folder with node modules and a package.json for our project configuration. We do not necessarily have to care about the post-install.js and the React Native CLI config file at the moment. The remaining folders are more important. There's the static assets folder that contains all external resources. In our case, this would be the equirectangular image. And there's the VR folder that contains code necessary for running the application, and an index.html file that will launch the application. So most of the time, we do not have to touch anything but the index.vr.js file or create new files. So this is the index.vr.js file. You see that we do not have to write much code to show the panoramic image. ReactVR already includes a pano component with a source property that we can use to locate the image and display it in the WebVR scene. And the pano component itself is nested in a view component, which acts as a container that provides support for touch input, layout features, or styling. I'll come back to this later. But yeah, it's almost boring, but that's all we need to show this spherical image in a stereoscopic way. If you are familiar with WebGL or Free.js, I guess you are amazed, because we usually need much more code to create a WebGL scene, the camera, the lighting, the sphere geometry, material, and so on and so on. And I guess it's probably a good moment to say thank you to the creators of ReactVR. I think I saw them. So thanks. It's really cool. I will show you more ReactVR code later, but first let's get back to the web and VR. We are in a kind of similar situation like we were in 2007 or 2008 when the iPhone and with it the first mobile sites appeared. So back then we had to reconsider how we present information on a tiny screen or on screens with various sizes and ratios. And now we have to think about how we present content to our user when there's no more separation between the user and the application. So our users are finally in our application. At our company, we try to get insights about this by using the example of an image gallery. So how would an image slider or gallery look if the user wasn't staring on a flat screen, but could be in the application? I think that the VR web comes hand in hand with losing our UX design metaphors, because we all agreed that an image gallery, one slider, would of course be a gallery with images in it. So this is my gallery prototype. You can look around and gaze at buttons and make the images scroll and move. And based on this example, I will show you some more ReactVR code. So here's a visualization of the component hierarchy. We have the index.vr.js file, which includes a lightning component and a UI component, a room component, and a gallery images component. And as you can see, the UI component, again, is the parent of another child component, the button component, and the room component contains a wall component, the gallery images component, a gallery image component. So we'll start with a look at the index.vr.js file here. Like you see, that like before, we first import the components and then render it with the JSX code that basically reflects the hierarchy I've just shown. So this is the lightning component. It's a bit more interesting because it uses two ReactVR components. First, there's an ambient light component, which is a light effect that affects all objects in a scene equally and from all directions. And there's a point light, which is a single point light source that spreads outwards in all directions. And with the property intensity, we regulate the power of the light sources. With the style property, we can modify the position, layout, and styling of the component. So now let's take a quick look at how the gallery room was made. So I wanted to create a room with a floor, obviously, and 4 walls, 1 solid in front of the user and 3 with windows around the user. And therefore, I created a simple default cube mesh in Blender with 2 materials, 1 solid and 1 for the window. And then to make a room out of it, the cube will be scaled and translated to the correct position in 3D space. So here you see the room component's child component, the wall component, and it uses another ReactVR component, the mesh component, that can be used to display 3D meshes in the wavefront OBJ file format, which I exported from Blender. As you can see, we use the property values from the parent component to set the material, transition, and scaling properties. Now, within the room component here, we just have to build a room by creating a floor, a solid wall, and the 3 walls around the user. So I guess you all know how React.js and working with components, props, and states work, most of all probably better than me. So let me tell you more about the VR-specific features of ReactVR. First, some things about scaling and the 3D coordinate system in general. So here you see that we scale a cube to a wall geometry by enlarging the x value, which is the width, to 5, and the y value, which is the height, to 3, and the z value, which is the depth of the wall, to 0.2. And then we move it 5 values backwards on the z-axis. Now, you may wonder why we have to move the solid wall we want the user to look at when launching the application in a negative backwards direction. This is because ReactVR uses the OpenGL 3D coordinate system, where the x-axis points horizontally to the right, like always, and the y-axis points up, and the z-axis points towards the user, while the user looks in the -z direction. And then 1 unit, or more precisely 1 distance or dimensional unit, corresponds to 1 meter. It's like miles, no, smaller. This is why we have to set the wall in front of the user to -5 meters in z direction. Now, okay, we talked about the 3D coordinate system. Let me show you another cool feature that we can use in ReactVR. It's the Flexbox layout. So to display the gallery images on the wall in front of the user in his horizontal row, we create a gallery image component that uses the React image component. And in the parent component, the gallery image component is used to create images dynamically and add them to an array, and then insert them in a ReactVR view component. By default, the view component uses a Flexbox style layout and displays all children with a flex direction column vertically one above the other. And to arrange the images horizontally next to each other, they just have to adjust the style property and use flex direction row. And again, that's it. Everybody here who's worked with WebGL or FreeJS knows that we would have to write much, much, much more code than here with ReactVR. It's really awesome. Which leads us to another great feature that we can use in ReactVR, the animations or the animated API. To animate the images to scroll in a horizontal way, we import the animated component, set a scroll value state in the constructor function, and then to simplify things here, animate the value within the component with will mount function. Then we can use this animated value within the translate transform style property as the X value, and voila, the animation will run when our gallery images component was loaded. Last but not least, let me introduce you to the other remaining ReactVR components and core components I didn't mention yet. I already introduced you view component and the image component, the pano, the mesh component, and of course the two light components. There is also the core component text component we can use to render text in our VR scene. And there are two more components that add light to a scene. A directional light that, like the point light, affects all objects in a scene equally, but this time from a given direction. And there's a spotlight, which is a light source from a single point, but it spreads outwards in a cone. Another really, really useful feature is the VR button that normalizes click and gaze events for headsets that don't support clicks. And yeah, to delight your users, you can use the sound component that adds audio to a coordinate in your 3D scene. Yeah, we could talk about this all day, but I think we should also take a closer look at UX design for virtual reality, because the way we interact with the digital world changes dramatically in VR. Bo Cronin has created the hierarchy of needs in virtual reality, which I find very compelling and a good guideline to prioritize our focus when creating VR apps. The hierarchy shows that the most important needs in VR are comfort and interpretability, and only afterwards comes usefulness and delightness of an application. So comfort means that the user can use our application without feeling unwell, and interpretability means that the virtual world feels convincing to a user. If both needs are satisfied, the user gets this feeling of actually being present in the virtual world, and this is what we want to achieve. Now, we cannot talk about all needs. I want to focus on comfort and begin with some facts about ergonomics. As we figured out, our VR application does not have a limited viewport. On the contrary, we have an infinite canvas, but our user has a limited field of view. And this field of view, of course, may change because a user can rotate her head and look around. So some smart people found out how big this field of view actually is. If a user is sitting, she can see a 70-degree circle in front. When turning the head comfortably around 30 degrees, or with stretching to max 80 degrees, the range a user sees increases to 230 degrees. Of course, we could bend and turn around much more, but this means that our main content should be within this range if we want our users to engage with it without effort. Another fact we have to remember is that we have the best depth experience if the content is not more than 20 meters away and not closer than half a meter, because everything closer than 50 centimeters will make us cross-eyed. And since the devices we have at the moment have a relatively low amount of pixels per degree, we also have to use large font sizes. Most designers agree that it should be more than 20 pixels. One word about PPD, which means pixels per degree. The devices at the moment have a relatively low amount of pixels per degree, like 10 PPD or 12 maybe, and a good resolution to not see any pixels anymore would be 60 pixels per degree. So you see there's a way to go before we can use smaller font sizes. Okay, now we know where to put our content to make it comfortably visible for a user. What can we do more to make our users comfortable? We can avoid eye strain by using darker colors, and we can avoid focusing on different depths. We can also avoid creating environments that may trigger phobias, like large empty rooms or small rooms, messy spaces, heights or underwater environments, or standing on a stage in front of many people. Yeah, we can avoid, we should always use correct scales. And we do not want to move things fast towards the camera, especially sharp or dangerous or gross things, I guess. We also do not want to attach things near or directly to the camera. Okay, now, what about the elephant in the room when we talk about comfort and VR? So what about simulation sickness? I guess making your users feel sick, causing them physical pain, or making him or her even throw up is hopefully the last thing you want to do as a developer. So how can we avoid motion sickness, or better, simulation sickness? Simulation sickness occurs when our sensory inputs are not consistent. For example, when the simulation tells us that we are in a car race, but we are actually just sitting still in a room. There are some best practices we can regard to avoid causing simulation sickness. First of all, don't use acceleration. And then do not move the horizon, or do not force movement to the user, which means do not move the camera. If you want to have animated scenes, you should allow additional head movement. For example, you can put the camera on a dolly and then animate the dolly. Also, always watch out for a low latency and, of course, a high frame rate, and avoid flicker and blur effects because they indicate movement. Then you can consider adding a stable focus point, and you should make your application support short usage by, for example, by saving states or making it offline capable. And also consider the use of more abstract patterns than realistic ones. For example, flying game controllers or cartoon hands will work much better than realistic arms and hands. Or another example is that a walking simulation will make more people sick than a flying spaceship simulation. This is because our brain knows really good how walking or our arms should feel like, and only a slight difference can make it confused and the user probably feels sick. So, if you like it or not, you as developers or designers, you are at least partly responsible for the well-being of your users. And with a VR web, we as developers may not only cause a low latency, low battery or high telephony costs anymore. With a VR web, we may cause actual physical or psychological pain. I mean, we talked about throwing up. A user could also run into walls or fall, or even worse, we could trigger paranoias or not prevent that scary or abusive material will be placed directly in front of a user's eye. And this is all way more serious in 3D, where we try to make our users think that they are in another world, and then this world hurts them. Also, on the other hand, I read about a study that let people be a superhero in VR, and then put these people and other people in a situation where someone needed help picking up accidentally dropped pencils. And the users who were a superhero in VR actually helped more often and faster than the others. So you see that your content and how it is presented matters, and this is why you all as developers matter. So be responsible and be aware while building VR apps. For you to read later, I have a list of resources if you're interested in ReactVR, and this is the URL to the slides, and also a newsletter I have about WebVR, so if you like, subscribe. And yeah, that's all. Thanks for your attention.